All right, hi everybody. This is a second video, second example of a net ionic equation. If you would like an additional example, I'm actually going to do kind of 1.5 examples in this video. The first one's going to be fairly quick though. I'm going to write the example of a synthesis reaction that is on your background information. So on the background information on the lab sims, you have an example synthesis equation of iron burning in oxygen to form, oops, this is my arrow over here, to form iron oxide. This is essentially the rusting reaction. Okay, so if this were the reaction that was happening in one of your in one of the reactions that you were doing for this lab, you might get this reaction, ba-boom, and then it asks you to write a net ionic equation. Well, in this case, remember net ionics, we split up things that are aqueous, okay, and then eliminate things that are the same on both sides. Well, in this case, there is nothing aqueous, so we cannot split anything up, okay, and nothing is exactly the same situation before as it was after. Sure, there's 4 irons, but this iron is by itself, it's a single element, whereas this iron is an iron ion in a compound, and it has a charge of +3. So the irons are not in the same situation. We cannot eliminate them. Same thing with the oxygen here. The oxygen over here is single element diatomic oxygen as a gas. Over here, he's now an oxygen ion, or an oxide ion, with a -2 charge in a solid. Okay, he's part of a compound. So none of the elements are the same on both sides. None of them can be split up. So you have 2 equations where this should happen on your virtual lab, where you end up with an equation where everything is solid or gas or liquid, and nothing will split up and nothing will cancel. That is fine. If there's no aqueous states, do not eliminate anything. You're done. That is your net ionic equation. Okay, so I wanted to show you that because I know there might be some confusion there. So if nothing eliminates, that's fine. That's your final equation. Nothing needs to change. Okay, the other type of equation you might possibly see is a precipitation reaction. So I wanted to show you an example of how to generate a net ionic equation for a precipitation reaction. So let's say that we were using our same silver nitrate. Okay, this is going to be a longer equation, so I'm going to try to make sure I use all my space here. So let's say I had AgNO3, aqueous. I'm in trouble writing AQ here. There we go. Okay, and let's say I react it with, say, sodium hydroxide, NaOH. And it's also aqueous. Okay, sorry, I don't have I couldn't round up the chemicals to actually do this one to show you. But let's say I have those 2 equations. Notice they're both aqueous, which means when we rewrite this in a second, we're going to split everything up. Okay? And then what's going to happen is typically positive ions, because they're positive, they're attracted. Opposites attract. Positives are going to attract negatives. Well, Ag was already with NO3, or, well, it kind of was, but it was dissociated by water, so it split up. But so he's not going to stick to NO3. The other negative he could go with is OH. So we say, okay, AgOH. You do need to crisscross your charges, but the nice thing is Ag and OH are both negatives, so no subscripts are needed here. Okay, and then the other things are going to be, we have NO3 and Na left. Okay, well, and one's negative, one's positive, so they would attract, and so they would kind of go together. By convention, we always put the positive first, so this would be NaNO3. Okay, we can use, even if we're not doing this reaction, we can use our solubility rules to determine what is going to happen for the states. Okay, so I'm going to try to get this focused enough for you. So you notice over here, come on, focus, there we go. So over here we have OH, okay? And then down here, I have AG. Okay, so AgOH is insoluble. If it is insoluble, that means that water cannot pull it apart. It is going to remain a solid. Okay, and then the NO3. So NO3 is easy. NO3 is right here in the top left. Na is a part of this row right here. There's an S. They're soluble. As FYI, all of these guys are always soluble all the way across. Okay, so they will always dissolve in water. Kind of same thing with these guys. These 4 ions right here are soluble all the way down. Okay, so anyway, the NO3 and the Na are soluble, and in fact, they are always soluble with no matter what you put them with. Okay, so this is going to be aqueous over here. Okay, hopefully it makes sense on how you predict your states. Okay, from here, we're then going to take, we're going to split everything up just like we did in the first example that I did in the previous video. So aqueous, we got to split it up because water, it means the water pulls it apart. So we get Ag, aqueous, plus NO3, aqueous. And I'm trying to write a little smaller so I don't run out of space because when you split stuff up, it kind of gets expanded. Remember, when you split them up, you do need to include states. You still need to include states. You also need to include charges because this isn't just silver now floating in the water. This is a silver ion. That's why the water could pull it apart, because it had a plus charge. This nitrate, same thing, except he's a negative. Okay, and then we're going to do the same thing for our NaOH. He's aqueous, so it's going to split up. We're going to have Na. I'm going to put a plus on him. And our OH, which is also aqueous. And notice I put the negative charge on OH. Okay, on the flip side. Sorry, there's some glare there, so, okay. Now you can hopefully see the arrow. On the right side of the arrow, we have AgOH, which is a solid. Reminder, if it's solid, water cannot split it up because it was insoluble, so we leave it together. So AgOH would remain together, unchanged by the by splitting the aqueous stuff because he's not aqueous. And then finally, we have NaNO3, who's aqueous. So we'd say Na positive aqueous plus NO3 negative aqueous. Okay, so here, again, the idea is the center arrow is essentially an equal sign. So if something is exactly the same before and after, we can eliminate it. Okay, the things that are the same before and after, we have an Na and an Na, so Na plus, aqueous, aqueous, those guys are the same. So we can eliminate them. Again, keep in mind they are still present in the reaction. That's why we have it up here in the full reaction. They are still present there, but they are simply spectator ions. They were floating around in the water prior to the reaction starting. They are still floating around in the water after the reaction has ended, so they remain unchanged by the reaction. Okay, so they're still there. Well, we're not removing them from the water, but all we're saying is that they didn't do anything in the reaction, so we take them out. Same idea with our NO3. So we have NO3 negative here. That's aqueous. NO3 negative aqueous over here. So we can eliminate it. It's another spectator ion. I actually like to use the example of sports here. Okay, because that's where we're familiar with spectators. Spectators watch the sports going on. Okay, and if you think about it, professional sports would not exist without spectators because professional sports, they make money playing sports. Where does that money come from? It comes from the spectators. The spectators are what makes that happen. So the spectators are necessary, but the spectators do not participate in the reaction. Okay, so that you can kind of imagine it like, say, NFL football game. And I realize things are different in COVID time, so just ignore that possibility. But let's say there's no TV to actually watch games and give money and anything like that. So it's just straight. You go to the stadium, you watch the football game, or you don't. The football game would not be able to occur like in a professional setting without spectators because they would not be able to make money. In fact, they would lose money. Okay, so without the spectators, the sport doesn't happen, but the spectators still don't actually play in the game. They don't participate in the game, so effectively they have no outcome, no effect on the outcome. Okay, so that's kind of the same thing that's happening here. Na and NO3, they are necessary to be present in order to get Ag and OH in the same reaction to react together, but they don't participate, so we kind of ignore their effect because they don't really have an effect other than allowing the reaction to occur. All right, so that's kind of my spiel on spectator ions. So after we eliminate those guys, Ag is still aqueous, OH is aqueous, and then we make AgOH. So you'll notice in this reaction, all that really occurs is an Ag and an OH find each other and they stick together and make a solid. That's all that really happens in this reaction. Okay, so that's all that really occurs in this reaction. But again, without the Na and the NO3, that would not be able to occur. But the Na and NO3 are unchanged. So they are eliminated from our final net ionic equation. So this is what your net ionic equation should look like for a precipitation or double replacement reaction. All right, well, hopefully all that makes sense, and I hope week 5 or the week 4-5 flip-flop virtual net ionic equation lab works out well for you, and everything is clear and whatnot. All right, have a great one, guys. Bye, y'all.